So you can start when you want.
So hello again, and now we continue our discussion of Billiard orbits and geodesics in non-integral flat dynamical systems by looking at the eigenvalue-based version of our shortline method. Like in the previous talk, this is joint work with Joseph Beck and his students Michael Dondas and Yushun Yang. Let us look at a one-direction geodesic on a flat surface in dimension 2. Let's say, consider the L-shaped region, which is made out of 3 squares like this. We can identify edges, the red with the red, the blue with the blue, the green with the green, and the brown with the brown, and that converts it into the L surface P that we discussed in the last talk. Let's look at a geodesic on P, where the slope is very precisely given. It is 1 plus root 2. Now 1 plus root 2 has a very special property because its continued fraction digits are all equal to 2. So let's look at this. Let's start with this very special example. This is the first D2 crossing of a vertical street. Remember, in this case, the vertical street is made up of the 2 squares on the left. And the D2 crossing is the inefficient way of crossing the street from left to right. The shortcut, which is in red, is a much more efficient way of doing it. Then we have the second D2 crossing and the second shortcut. And we see that the slope of the shortcut is alpha minus 2, which is square root 2 minus 1, which so happens also to be 1 over alpha. Right. And its continued fraction digits are 2, except that it doesn't have an integer part. So when we put together the almost vertical D2 crossings, one after another, we obtain an almost vertical geodesic V of slope alpha. And when we put together all the shortcuts, we get the short line H, which is of slope 1 over alpha. Let's now assume that V starts from some vertex of the L surface P. Then the short line itself is a geodesic of slope alpha. It has its own short line, which is almost vertical, and has slope alpha. And I want to remind you again that almost vertical simply means that the slope is bigger than 1, and almost horizontal simply means that the slope is between 0 and 1. So clearly, V and H are short lines of each other. And if we apply the short line process twice, we are back to the original geodesic. This means that we can use 2-generation short lines to understand geodesics, or going in the other direction, we can use 2-generation ancestors to understand geodesics. So let's talk a little bit about ancestors. Well, there are 6 different types of almost vertical units in the L surface. We've shown them here. They all go from one horizontal edge to another horizontal edge, 3 of them don't hit the vertical edge in between, whereas the other 3 hit the vertical edge somewhere in the middle. We can also talk about almost horizontal units, which are given in red. And again, 3 of them don't hit the horizontal edge, whereas 3 of them do. Now, here we have all these names that are given here, H1, H3, H2, H2. Please don't worry about them. I need them just to illustrate some points, and we don't really need to remember their names after maybe the next slide or so. So let's think about the ancestor process. We've already talked about this in the first talk, but here we want to be a little bit more detailed. Let's look at the picture on the left. We have the light blue, rather thick, almost vertical unit, which goes from an edge H1 to an edge H2. And we want to list its various ancestors. So we want to, first of all, work out the D2 crossing, for which the light blue, almost vertical unit is the shortcut. And the D2 crossing consists of a few parts. The red part, just a little bit of it, the green one, the purple one, and finally the blue one, just a part of it. And in the picture on the right, there's a little less. Now, what we are going to do is we consider one almost vertical unit, work out its ancestors, then we take the next almost vertical unit, work out its ancestors, and the next almost vertical unit, and work out its ancestors. But each time there's a fractional ancestor at the front and a fractional ancestor at the back. And if we count them both, that means we will be overcounting. For example, this red one is counted at the beginning here, right? But it's counted at the end of the previous ancestor process when we look at the almost vertical unit that comes before the one that we've drawn here. So there's a little bit of bookkeeping to do. So there are 2 ways to do the bookkeeping. One of them is to forget about the fractional unit at the end. So like in the picture on the left, we forget about V1, V3, V1 star, and in the one on the right, we forget about V1, V3. And we keep the others. An alternative is delete the first one and keep the last one. Whichever way, we count everything precisely once. Now let's use the delete n rule and work out the ancestors of all the almost vertical units given here. Right? Again, don't worry about what they are. This is just something that I've listed here. Now this information can be represented by a transition matrix M1 given here. Right? So for example, in row 1 and column 2, it tells us that one of the ancestors of H1, H2 is V1, V3. Next, let us use the keep n rule to work out all the ancestors of the almost horizontal units. There's a V1, V2, and so on. And we get another transition matrix, which is slightly different from the first one, right? Because we are now keeping the units at one end rather than the other. Now, let's start with an almost vertical geodesic from the bottom left vertex of the L shape. The first almost vertical unit is H1, H3. Now, H1, H3 is the second one on our list, right? So we can write down a coefficient vector and have an entry 1 as the second entry. That tells us that there is one unit of H1, H3 and no unit of any other kind. So W0 is just a coefficient vector, right? Now we start with H1, H3, and we now go and work out its ancestors. And we start with each of the ancestor units and work out its ancestors and keep on doing that. So let's start with W0, go for one ancestor. That means we have to multiply by M1, do another ancestor process, which means multiply by M2, do another one, which is multiplication by M1, and then M2, M1, M2. And let's do it k times. So we end up with a 2k generation ancestor units, right? And the number of each kind of them is described by the coefficient vector wk. And wk is related to W0 in this way. And if we so choose to have these coefficient vectors as column vectors, then we simply take the transpose of everything. Well, this gives rise to a two-step transition matrix, which is M2 transpose, M1 transpose, and in this special case of the L surface, this is the matrix that we're given. Let's now calculate its eigenvalues. This has 6 eigenvalues. The largest one is λ1 given here. The second largest one is λ2, and there are 4 more. But notice that λ1, particularly if you look at the square root of λ1, square root of λ1 is 1 plus root 2, and the continued fraction is 2, 2, 2, 2, 2, and so on. Let us look at λ2. If you look at the square root of λ2, we might be a little surprised to find that the continued fraction is 1, 1, 1, 1, and so on. So it looks like they were started from 2, 2, 2, and just half each digit to end up with 1, 1, 1, 1. Is this really the case? Right? That is the question. Well, what Beck, Donders, and Yang managed to prove is the following. Let's suppose that we have a geodesic with slope alpha, which is 1 plus root 2. Take an arbitrary convex set on a square face of the L surface P. Let's suppose that we persevere with this geodesic up to time capital T. And let us see how much time this initial section of the geodesic spent in the set S, and compare that to the expectation. The expectation is area of S times T divided by 3. What they can show is that this is bounded by a constant times T to an exponent kappa naught, which is smaller than 1. And indeed, the exponent kappa naught is obtained in terms of these two largest eigenvalues, lambda 1 and lambda 2. And we see that the continued fraction of 1 plus root 5 over 2, which comes from lambda 2, is obtained from the other continued fraction by digit halving. Furthermore, the error term big O of t to the kappa naught is actually sharp. It's not, one cannot improve it. Furthermore, Beck, Donders, and Yang consider not just 1 plus root 2, but they consider slopes of the form k plus square root of k squared plus 1. That has the property that the continued fraction expansion has digits all equal to 2k. And they perform a similar exercise and end up with similar conclusions. The constant kappa naught, which now depends on k, is obtained using the two largest eigenvalues, or the two eigenvalues with the largest absolute values of some suitable transition matrix AK. And the error term is sharp. They went further. They actually considered a geodesic with an arbitrary slope gamma, which is a quadratic irrational. Now, for a quadratic irrational, if we write out the continued fraction expansion, it becomes periodic eventually. Now, we want to make sure that every continued fraction digit is even. So here we have a 2 everywhere. Right? And they can consider some appropriate transition matrix, and lambda 1 and lambda 2 are the eigenvalues of this matrix with the largest absolute values. And using these two eigenvalues, they can calculate this quantity kappa naught, which is called the irregularity exponent. And there is a simpler way you can find these eigenvalues, lambda 1 and lambda 2, given here. They are eigenvalues of smaller matrices. Now, how about uniformity? Let's suppose that we have an arbitrary convex set on a square face of the L surface P. Suppose that the irregularity exponent is positive, like in the case when alpha is 1 plus root 2. Then again, we have uniformity in a similar sort of format, where the error term is big O of t to the kappa naught, and the error term is sharp. On the other hand, if the irregularity exponent is equal to 0, then one gets even more. One gets what one might call super uniformity, because the error term is now logarithmic in size. Now, gamma, the slope, has every continued fraction digit being even. How about a finite polysquare surface where the street LCM is H? Remember, the street LCM is the least common multiple of the length of all the horizontal streets and all the vertical streets of the finite polysquare surface. right? For the L surface, this is equal to 2. So we're now replacing 2 by h. So if we take gamma to be a quadratic irrational, where the continued fraction digits are all divisible by h, then we have similar results. We can calculate the appropriate transition matrix and the eigenvalues, the two largest one, or the two with the largest absolute values, calculate the irregularity exponent, and go on to describe time quantitative equal distribution with respect to all convex sets. I haven't written down all the details here. Next, let us look at a square face of a polysquare surface P. Corresponding to each square face, there are two types of almost vertical units. They're given in blue. They go from the bottom edge. They go from a horizontal edge to another horizontal edge. One of them doesn't hit the vertical edge in between, and the other one crosses a vertical edge into another square face. And we also have two types of almost horizontal units. Let D be the number of square faces of a polysquare surface P. Now D is equal to 3 for the L surface. And since there are two types of almost vertical units for each square face, that's why the L surface has 6 almost vertical units, or 6 types of almost vertical units and 6 types of almost horizontal units. But now if we have D square faces, then we have 2D of each kind, which means that the transition matrix is now 2D by 2D. Let's look at a problem. If we want to study geodesics on the cube surface, then in the last lecture, we've already shown that this is equivalent to studying one direction geodesic on a surface that looks like this, that has 24 faces, which means that we end up with a 48 by 48 transition matrix, which is a rather large transition matrix, not something where one would calculate the eigenvalues by hand, right? One may use MATLAB, but that's still not very nice, right? We would like to have some way, some simpler way of getting the two critical eigenvalues. So let's look at a polysquare surface P with D square faces, and let's consider an almost vertical geodesic V0. Let's say starting from a vertex in P, and the slope alpha has continued fraction expansion n, m, n, m, and so on. V0 is made up of 2D types of almost vertical units of slope alpha. So we are really thinking about a vector space W with a basis consisting of the 2D types of almost vertical units. Let's look at the short line H0. It is almost horizontal, and it is made up of 2D types of almost horizontal units. So we are thinking here of a vector space W prime with a basis made up of 2D almost horizontal units. And if we look at the short line of H0, we go back to V0, and we are back to the space W with basis script W. So let's start from the bottom and work our way up, back up. Right. So the first step of the ancestor process would take us from the basis script W to script W prime. And let's say the coefficient vectors are taken as column vectors. Then we have a 2D by 2D transition matrix. The second step of the ancestor process gives us another transition matrix. And the two-step ancestor process gives rise to a transition matrix, which is the product of these two transition matrix M1T and M2T. And let us look at this matrix A. It has its eigenvalues, perhaps with multiplicity, and let's list them according to their absolute value. And the multiplicities clearly add up to 2D. So we are talking about the coefficient vectors would end up in a space C raised to the power 2D. And this can be written as a direct sum of A invariant subspaces of C to the 2D. And these invariant subspaces Wi would each contain an eigenvector psi I corresponding to the eigenvalue lambda I. Suppose that di is equal to 1, then clearly psi I generates the whole of Wi. On the other hand, if the multiplicity is bigger than 1, well, we still have at least one eigenvector, right? But we can put in a few other vectors and make a basis out of that. And so we end up with a basis of Wi also. And putting the bases of all these different Wi's together, we obtain a basis of C to the 2D. V0 starts at a vertex of P with a finite succession of almost vertical units. And let's suppose the coefficient vector of these almost vertical units with respect to the basis W is given by W0. Obviously, we can write W0 as a linear combination of the basis elements of C to D. Let us now take part in the ancestor process. We go for the R generation ancestors. So R would be equal to 2K, right, from our earlier discussion. And after that, we are supposed to end up with the coefficient vector WR, which is written in this way. Right? We just multiply by AR. Let us make some assumptions. Let us suppose that for the large eigenvalues, large meaning that the absolute value is bigger than 1, then the corresponding basis of Wi consists only of eigenvectors. And we don't care about what happens for the others. In this case, we can write WR as a sum plus some error, the sum consisting only of information of these large eigenvalues. And the bounded error comes from the remaining small eigenvalues. Of course, when R is large, then this main term dominates and the error is small. And it's quite clear that the main term and the main error term correspond to the two largest eigenvalues. So That's our lambda 1 and lambda 2. Now, how about a simpler way of finding these crucial eigenvalues? Because we only want the largest 2 eigenvalues, maybe even the next one, but certainly we are not interested in the small ones. So is there a way where we can find these crucial eigenvalues while ignoring those that we don't need to know about? Let's suppose that H is the number of horizontal streets in the polysquare surface P. We can show that we can find an A invariant subspace of C to the 2D with the following properties. First of all, we can explicitly write down its generators, and there are only at most 2H of them. Secondly, this subspace contains all the eigenvectors that we want to know about. In fact, our technique gives rise to what we call a street spreading matrix, which is of size H plus H. Now, think about the question when we were looking at the geodesic on the surface of a cube. The transition matrix is 48 times 48. As it turns out, the street spreading matrix, the corresponding street spreading matrix is actually 6 times 6, which is a lot smaller. Now, we can calculate the eigenvalues and eigenvectors of this H by H matrix. Then there is another matrix that is 2H by 2H, and the algorithm allows us to calculate the eigenvalues and eigenvectors of that. And from that, we can actually find the relevant eigenvalues and eigenvectors of the original matrix A. Right? This is a lot simpler. Right? Now, to actually get any of them explicitly, we need to do a fair bit of calculation, and it's too long to illustrate it here. Also, to justify the algorithm, it is a rather lengthy argument. So again, we are going to leave that, and I'm afraid that I have to ask you to take this on trust. Okay, we now move to another rather different question. Let's play billiard in a right triangle with the angle pi over 8. So it looks like this. Unfolding means that we try to convert this to a problem concerning a one-direction geodesic on some surface. And it turns out that we can unfold it to a problem concerning one-directional geodesic on the regular octagon surface. So here, this means that we just have to study this problem of a one-directional geodesic, and we have the answer for the billiard as well in the right triangle. So let's look at the problem of one-direction geodesic on the regular octagon surface. Well, let's look at the octagon. Let's take the yellow triangle on the bottom left and move it to the top right. Remember, because this is a regular octagon surface, the edge between 3 and 7 plus is identified with the diagonal edge and 7 minus. So that's why we can move the 7 minus to where 7 plus is. Similarly, we can move the green one from the bottom right to the top left. And furthermore, we can move the blue rectangle to the right on the top as well. And after we've reshaped this regular octagon surface, we end up with a surface that is made up of 3 rectangles. And it doesn't take much to realize that the 3 rectangles are similar. We can look at almost horizontal detour crossings, shown in red, and the almost vertical shortcuts. And this is an example of what we call a street rational polyrectangle surface. Now we need to explain the term street rational. That simply means that the ratios are rational multiples of each other in some sense. Right? The concept that we want to look at is that instead of thinking of the length of a particular street, right? In a polysquare surface, the length of a street is just a number of squares in that street, right? Here is a little bit more subtle. We consider a concept which we call the normalized horizontal street length, which is actually the length of the street divided by the width. Now, if we look at the surface, the polyrectangle surface that describes the regular octagon surface, right? We see that the normalized horizontal street lengths are 2 times 1 plus root 2. That's the street made out of the 2 rectangles at the top. And the length of the other street is 1 plus root 2. That's the bigger rectangle at the bottom. We can consider a quantity which is called a normalized horizontal street LCM, least common multiple. And this is the smallest integer multiple of all the normalized horizontal street lengths. And in this example, H star is 2 times 1 plus root 2. We can do the same exercise with vertical streets. So we have these 2 quantities, H star and V star. And using these 2 quantities, we can write down some slopes that we can work with. And in fact, we want to start with geodesics that have slope alpha equal to this quantity. So the V star and H star now play the role of the 2 and the H and all the other things in the other discussion. And so we have the following result. Let's start with a finite street rational polyrectangle surface. There are infinitely many explicitly given slopes alpha, such that if we consider one direction geodesics with these slopes, we first of all can establish superdensity. Secondly, we can compute the irregularity exponent. And using the irregularity exponent, we can give time quantitative equal distribution of the geodesic relative to all convex sets. Here, I haven't written down the details. Now, remember, the regular octagon surface was viewed as a finite street rational polyrectangle surface. Therefore, we have the same result for the regular octagon surface, and we can see that a similar argument will give similar results for a regular polygon surface with an even number of sides greater than or equal to 8. Now, I would like the reader to think about the audience to think about what happens in the case k equals 6. Now, given that we can work out what happens to the one direction geodesics in the octagon surface, we can translate this result back to Billet in the right triangle with angle pi over k for even k greater than or equal to 8. Right? The similar sort of results, the whole raft of them: superdensity, irregularity exponent, and time quantitative equal distribution relative to all convex sets. Next, again, I ask the question, what happens when k equals 6? Next, how about playing billiard in the regular octagon region? Well, let's have a first look. Do a little bit of partial unfolding to see what happens. Start with the left regular octagon, and then we can construct the one on the right by a mirror image. And a little thought would end up with the following conclusion. If we start with billiard in the regular octagon region, it is equivalent to studying one direction geodesics on this surface, which is made up of 8 regular octagon faces. Now let's look at this surface. I've listed all the edge identifications here as well, and I only need some of them to explain to you what's going on. Here is a street. It starts on the top left, where we have the edge C3. It goes along 1 prime, then goes to 2 prime and 3 prime. And using the edge identification B2, it goes to 4 prime. And using the edge identification G3, it goes to 5 prime, and so on. And eventually goes to 8 prime and ends back up in 1 prime. So this is a finite street, a street of finite length. This is one street in the direction shown. The blue one is another street. The green one is a third one. It's a little narrower, but nevertheless, it is a street. And we have yet another one in purple. Now, we can chop up each of the red polygons into 2 triangles and 2 squares. And we can chop up each of the, say, green triangles into 2 triangles. And using edge identification, move them around and rearrange them. And if we do that, it takes a little bit of time to get it right, but if we do it, we can end up with something that looks like this. This is a street rational polyrectangle surface. What does this tell us? That tells us that by playing billiard in the regular k-gon for k greater than or equal to 6, we have superdensity, we can compute the irregularity exponent, and we have time quantitative equal distribution. Next, let us play billiard in a right triangle with angle pi over 5. It turns out that using unfolding, we can reduce the problem to a problem concerning one direction geodesic on the regular double pentagon surface. A double pentagon, not a single one, double pentagon surface. So now let us look at one direction geodesics on the regular double pentagon surface. Again, moving the triangle C from the bottom left to the top right, and moving the triangle, the yellow triangle from the bottom left to the top right, and moving the green triangle from below to above, we end up with the figure on the right, which is a street rational polyparallelogram surface. Now, it's a mouthful saying polyparallelogram surface, but really it is just a polyrectangle surface in disguise. We've just kind of twisted it a little bit, that's all. So we just visualize it as a street rational polyrectangle surface. There's no different one from the other. So we have a corresponding result concerning superdensity. We can compute the irregularity exponent, and we can describe time quantitative equal distribution. And therefore, we can also describe Billet in the right triangle with angle pi over 5 or angle pi over k for any odd k greater than or equal to 5. We have a similar sort of results. Next, how about Billet in the regular pentagon region? We reflect one to get the other here, and that suggests that we keep on reflecting. And if we do that, we can actually show that Billet in the regular pentagon region is equivalent to one direction geodesic on this surface that's made up of 10 regular pentagon faces. We can look at a street in this direction, another street, and then in another direction, cut up the various pieces into smaller pieces and start rearranging them by using edge identification, ends up with a picture like this. So we end up with a street rational polyparallelogram surface, which is really just a polyrectangle surface in disguise. So again, we have superdensity, right? There are infinitely many slopes where we have superdensity. We can calculate the irregularity exponent, and using that, we can describe time quantitative equal distribution with respect to all convex sets. The next question that we want to look at is geodesics on the surfaces of the Platonic solids. The first Platonic solid is the regular tetrahedron surface. That's an integrable system. The next one is on the cube surface, and we've discussed that already. The third one is on the regular dodecahedron surface. Now, the standard net of the regular dodecahedron surface has 12 regular pentagons. And if we play, remember that if we play Billiard on a regular pentagon, we end up with a one-directional geodesic in a surface that has 10 regular pentagon faces. So if we start with 12, we end up with 120. So the problem is a problem of one direction geodesic on a surface with 120 regular pentagon faces. And we can handle that too. The other two remaining Platonic solids are the Octahedron and Icosahedron. And for these surfaces, we are actually looking at polytriangle surfaces. They are made up of triangles. Let's look at one of them. Geodesic on the regular octahedron surface. Now, this surface has 4 pairs of vertex disjoint faces that I've labeled them 1, 5, 2, 6, 3, 7, and 4, 8. And between any pair, we can actually work out a street. And there are 4 streets illustrated here. And we end up with a street rational polyparallelogram surface. And we already know that we can handle them. This shows the detour crossings, shortcuts. Next, let's look at Billet on the 60-degree rhombus, which is the shaded part in the picture on the left. Unfolding takes this to a problem of one direction geodesic on this surface. We can label these triangles that made up this surface, and I've conveniently put down some of the edge identifications, because using this we can see that there is a street that is made up of the triangle T11, T12, T21, and then using the edge identification C3, go down to T32, then T31 and T22, and we can see from the edge identification D3 that it goes back to T11. So this is a street, right? But this again gives us a polyrectangle surface. Here we've shown some streets, and the streets on the left picture can be put in the right picture like this. So our result is the following. If we have a finite polytriangle surface and we look at geodesics with slope alpha, then there are infinitely many explicitly given slopes alpha where we can obtain superdensity, calculate the irregularity exponent, and describe the time quantitative equidistribution. And also, we can play Billiard with the same results. Next, we claim that our short line method works for all Veitch surfaces. What is a Veitch surface? Well, Veitch discussed a class of surfaces that have the following properties. First of all, there's street rational decomposition in any direction with rational slope. Secondly, the one direction geodesics are either uniformly distributed or periodic. There's this dichotomy, and this property is sometimes known as optimality. There are many examples of Veitch surfaces, or the polysquare surfaces that we've discussed earlier, polytriangle surfaces, these surfaces translation surfaces that we obtain from playing billiards in regular polygons, and there are others. A very interesting one is the class of cathedral surfaces that were discovered by Mcmullen, Mcmullen, and Wright 3 years ago. Right. Each of those consists of 5 horizontal streets and 5 vertical streets. Now let's look at the ratio of the length over the width of these horizontal streets. We can calculate the ratios that are given on the right. So what Mcmullen, Mcmullen, and Wright did was to look at values of A and B, which make these ratios to be rational multiples of each other. And they found that if we take A and B in terms of two rational numbers R1 and R2 and a square free integer d in the way that is given, then all these ratios are rational multiples of each other. And the same goes for all the vertical streets. They're rational multiples of each other. Now, what does that tell us? That tells us that our method works on all cathedral surfaces and gives us superdensity, irregularity exponent, and time quantitative equal distribution for infinitely many explicitly given slopes alpha. Some years ago, Mcmullen actually classified all Veitch surfaces of genus 2. There are only two types. One of them is the regular decagon surface with parallel edge identification. Well, that was something we discussed earlier, where k is even and equal to 10. Right? The other class are what is called the Coulter-Mcmullen L staircases. They are actually generalizations of the L-shaped region and the L surface. So what happens is that if we take A and B, the lengths, describe them in terms of two rational numbers R1 and R2, and a square free integer d, then we have street rational polyrectangle surfaces. And since they are street rational polyrectangle surfaces, our method works. So there are infinitely many given slopes where we have all the various properties that we alluded to. And we can play Billiard as well as one-direction geodesics. I want to end by discussing a family of genus 2 non-regular decagon surfaces. So these are width 2 and height 2. And because they are non-regular, the classification result of Mcmullen tells us that these surfaces are not Veitch surfaces. Now, it is not difficult to show that there are infinitely many values of A, B, and C, which gives rise to street rational polyrectangle surfaces. But the fact that they are not Veitch tells us a bit more. First of all, there's a result of Mcmullen that says that if a translation surface of genus 2 is not Veitch, then you can find geodesics that are neither dense nor periodic. Then there's another result by Chen and Mesa a year later, which says that under such conditions, we can find geodesics that are dense but not equal distributed. But now, let us apply our short line method. Then we can show that there are geodesics that are super dense, and also there are geodesics that have time quantitative equal distribution. So for this class, this family of genus 2 non-regular decagon surfaces, there are all sorts of geodesics with different properties. And on this note, I shall finish. Thank you.